Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Luthfi Ardien, and today I'm gonna be reviewing about uh, yesterday's UAS of mechanical fluids. So let's just get started. First, the question talks about an orifice meter. Basically, it's airflow up to 1 meter cubics per second at standard condition expected of 0.25 diameter duct. So basically, this the diameter of like the pipe, the big area is 0.25. The orifice meter is used to measure rate of flow. Basically, measure this rate of flow. Basically, this one, like the rate of flow of how the flow fluid is flowing to the orifice. But basically, I want to refresh the knowledge. If you didn't know, orifice is basically like a pipe which has this section right here. So basically, it's like 90 degrees of wall, and compared to like Venturi, it has a really high head loss, but the initial cost is very low. Basically, so for efficient purposes, Arfis is not that very effective, but so if we want to get the efficient purposes, we will probably have to get Venturi because the head loss is pretty minimum, but the initial cost is bigger. So if you want, so basically, yeah. Let's get that out of the way, shall we? We want to solve this problem. Okay, so basically, my intention is I hereby want to solve this Maxwell equation about flow through an Arvis method because I want to evaluate my knowledge on this topic. So basically, I want to determine the head loss of the flow area if the specifications are in this part right here. So basically, this is my initial thinking. I draw the orifice and then with the specifications, and I assume it's a steady flow and also a incompressible flow. And with this come in mind, I had thought the idea that I will use the Bernoulli equation and also the continuity equation, which is the conservation of mass, basically conservation of mass equations. And here are the idealization. So basically, the Bernoulli idealization, I transform it. So basically, I neglect this part right here, the gravity, not the gravity, but the z. The z are all the same. So we just like just get that out of the way, and also this one right here we get out of the way, and then we get to this part right here, which comes to this equation, which delta p. This is delta p. Delta p is basically the difference in between temperature pressure. This part right here is gonna be our equation for the next part. And also the continuity idealization, also we we uh, we strip the we strip the raw, and then we get this v1 divided by v2 equals to a2 divided by a1. And after that, we can combine this all into this part right here, which we can combine into v2 equals to this right here. And then we can do like this. We can use the mass conservation of mass equation, which is I forgot the English for massa jenis. Wait a minute. Yeah, rho times v, which is velocity of the flow, and then times the area of the flow. Basically, the area of this part right here. We can use diameters, which since it is orifice, basically we just assume it's a circle, and that will get to v times d squared divided by 4. Yeah. So yeah, we actually substitute the v2 here, and then we get to this the final conservation of mass equation, which is right here. So let's get to the instruction real quick. Okay, so basically, this part I'm gonna do an analysis for the Reynolds. I'm gonna do an analysis of the Reynolds number with this graph right here. So this graph I got from Padai, which is when Reynolds number is this, the orifice number is this. So basically, it's just like a perbandingan between this and this. So yeah, we got this right here. The Reynolds equation is basically this. And since this is a standard condition, we just assume the air density and air viscosity, which is this and this. We can get this right here. Can get the Reynolds, which is 3.5 times 10 5. Okay, so we get that part, and then let's keep that for now, and then we get to this part right here, which is beta. Beta is basically a ratio of d2 divided by d1, and then we get this is basically at this part is basically an initial guessing game. So basically, we want to like guess on the on how big is the pipe is. So I assume is to be, so basically I here guess it's 0.165 meters, and then basically we got the beta is 0.66, and then we get to this part right here, which actually is this part. From this part we get this density. Finally, I know the English of massa jenis. Density times 1 minus beta of 24 divided by 2 times this part, and then we get the pressure, the delta pressure, which is 2830 PA. Okay, then we do a head loss analysis. So we neglect this and this because basically the part we want to analyze is at this point and then at this point. So basically the pipe conditions are all the same, but the fluid is different. After the fluid hit this part, there's gonna be a head loss because basically in mechanical fluids, from our previous lesson when we analyze and when analyze inventory, we don't actually like determine the head loss because it's so minimum. But for this part, we really need to determine it because head loss for orifice is so significant that we have to determine it. Basically, we from the Bernoulli equation we get to the head loss part, which is right here, and then this we get to this. We neglect this part, and then we get this part, which is the head loss and equation, and we get to substitute it with adding P2 minus P2, basically 0, but we substitute it with make this equation right here, and then yeah, basically that's the head loss equation for now. And right now I'm gonna do analysis for at point of 0, 2, and 3, which is pressure from 3 and 2, and this part is the equation 0.65. Basically, where's the 0.65? It's from this part right here. So if the flow area at vena contracta is 0.65 orifice diameter, so yeah, that's the 0.65 beta squared, and then this. We get the pressure difference is 1290. And then we can actually do some head loss. We can substitute those numbers into the head loss equation, and we get 1250 newtons meter. Okay, so let's analyze it, shall we? Okay, so we got the head loss. Basically, this is a head loss ratio, which to determine how big is the head loss. So basically, P1 minus P3 divided by P1 minus P2, which is 1250 divided by 2830, which equals to 0.44, which we can times 100 equals to 44% head loss. Okay, that's for number one. And then number two, basically it's a spray head, which if we have at home, like sort of a spray like for gardening and stuff like that. So basically that's the part we're going to analyze. So there's a pump, which is right here, the pump that supplied through 500 feet of drawn aluminum tubing from engine during pump. In its most efficient operating range, the pump output is 1500 GPM. Basically, the water that comes out, the water that the water that comes out from the system is 1500 GPM. And then there's this part right here, at discharge pressure not exceeding 65 PSEG, which is, yeah, well that means the pressure should not be exceeding 65. That means it should be below or equals to 65 right here. But the sprinkler right here must operate at 30 PSIG, which we can assume it should be operating equals to 30 or more than that, which we can assume the difference in pressure, which is going to be 35 if we like 65 and minus 30. But assuming this part and this part, the pressure will be equals to 35 or sorry, or lower than 35. And then we get, because this is drawn to being the E equals to, basically E is a roughness for the pipe system. Actually, for the tubing system, this is basically the roughness, 5 times 6, 10 to minus 6 feet. Yeah, that's it. So we get to this part right here, where basically this is a pressure analysis, which we can use Bernoulli equation to it. And for the realization, I just assume this is a head loss analysis again, same as number one, which we can neglect this, and neglect this, because basically it's at this point and then this point. This is basically the same type of profile for the basically same space, same, like, yeah, you get the point. So yeah, we neglect that, and then we get to this part, which is the equation, which equals to this right here. And then some substituting methods, which equals to this part right here. Okay, we got the equation, the final equation we need, and we just do the instructions real quick, which is, first we actually convert this into feet cubic per second by first minutes to seconds, which is divided by 60, and then gallons to feet cubics is basically divided by 7.48. We got 3.34 feet cubics per second. So basically this part right here is just guessing. For my guess first is the pipe should be at 6. Oh yeah, basically this part actually asks what is the small standard pipe size that can be used. So 6, I assume it to be 6 first, and then we get to the Reynolds equation, Reynolds analysis, which is going to be this equals to this. And we can see to the Moody chart, or basically just do some calculations, which E divided by D equals to, D is basically the diameter, 6, which is, so if we see at the point, so 5 divided by 6, 5 times 10 minus 6 equals to that, yes, 1.10. And then we get to this part right here, we get the mood. Basically you can use these calculations, which is kind of played, or we can just assume from the Moody chart we get to this point right here. And then we got this, we got the F equals to this, and then we can determine it from the pressure analysis equation, which is this part right here, this part right here equals to this. So if we analyze it real quick from this part, where, yeah, this part, the pressure, the difference in pressure should not be lower, or should be lower or equals to 35. Basically 24 is lower, so basically it's correct, but I'm going to guess again. I'm going to go lower, which is 5 in. I assume it to be 5 in, and basically the pressure is too high. Because the pressure is too high, it's not capable, so it's not efficient, the pipe to be 5 in. So basically the criteria for this is 6 in. Okay, so number 3 is we want to actually define the time required for the machine to decelerate from 270 miles per hour to 100 miles per hour, which with the machine as a dragster weighing about 1,600 lbf, with a parachute to actually decelerate the vehicle from 270 miles per hour to 100 miles per hour with an area of 25 feet squared. Okay, so basically my intention here, I want to find time required. This is time required to decelerate from 270 to 100 miles per hour with given conditions. Initial thinking. Okay, so this is basically the simple drawing, basically of free body diagram drawing. So basically the car is going that way, and also there is a parachute dragging the car backwards, which is FD right here. And then this is the numbers given, and we can basically assume, basically for drag force, the dimensional analysis is this part. And we can, since this is a force, I assume that I'm gonna bring the good old physics equation, which is F equals m times a. This is the general force equation. So basically this is a equation for force in general. So basically for the realization, this part right here, I'm gonna do a dimensional analysis, which is using Buckingham theorem, which equals to this CD equals to FD divided by half of density times V squared times A. Yes, sorry, I forgot the English. So yeah, we can actually move this part right here, this to there, to the instructions part, and we get to this part, FD. So basically the drag force equals to CD times that, and equals to MA, which we can get. Basically this is the force, the drag force. This is for the vehicle, and A is basically a derivative of dv per dt. So yeah, we can like substitute into this, and then we move it, sort it out into this part right here, which we can integral it to an equation we get to determine the time to decelerate, which is this part right here. Basically, we just put in numbers and then we get it's 5.05 seconds. Okay, number 4. Basically the picture here is not given on what it wants to determine, but actually as pada what will we determine from this, which is going to be actually the flow moving speed. So basically based on the given part right here, I want to analyze the wave speed. Yeah, so the initial thing, I just draw the wave real quick. Basically, for this, you can basically use continuity equation, which from continuity equation, which we can we can use idealization for transforming it into a sort of specific type of equation that we want to find, which is delta v. Delta v is basically a change in velocity equals to c times delta y divided by y plus delta y. Delta y is basically the difference in the highest part of the fluid in open channel flow to the lowest surface. Yeah, so this part and this part, and then the deep, and then yeah. So yeah. After that, we go into the hydrostatic force analysis, which Fx equals to Fr left minus Fr right, which we can substitute into this and substitute again, which is equals to this. X and Fsx we can actually define as this, which we can do this equals to this part right here, and we can like eliminate all the unnecessary components into this part right here, and then eliminate and then actually sederhanain, I forgot the English of sederhanain, to this part right here, which is c squared equals to gy, and yeah, and then we can actually move the squared into this to a root of this equation right here. Basically, in general cases, we just take this, the g and y. So basically we neglect this and we just take the g and y into where we can put it into an analysis for which is called a Froude number, which is v divided by c, which is the square of gy. Okay, so number 5, which is a choke flow in a converging nozzle. Basically, this is a flow which is an incompressible flow. Compressible flow. Basically, here it all revolves around Mach number analysis. So this is, I want to find basically what the question is. The question is to determine the Mach number at this part right here, the throat, and then the mass flow rate, and then the throat area to be determined. Okay, so this is my intention, and then this is my initial thinking, which since a compressible flow, I thought it to be a Mach number analysis, and also so this is also like an airflows, which I assume this is since this is airflow, a mass flow equation is required also. So basic for idealization, I want to determine if the flow is choke or not. So basically it's entropic flow analysis, which it as this part right here, which we can get to this part right here for a ratio. It is actually a choke flow, which if it's a choke flow, we can actually determine the Mach number is equals to 1. And then for the instructions, which we can use this from the Mach number equation, equals to c1 is equals to this, and then we can get the velocity is 570 feet per second, and we want to get the density of it, which is this part right here, which equals to 0.324 lbm per feet cubics. And we can get to the mass flow rate part right here, which equals to 2.4 lbm per second. Okay, so for the area of the throat analysis, we can use a ratio thing, and we can use the equation right here equals to this. We put numbers and then we get 1.303. Since this is choke flow, the A throat equals to A. Basically AT equals to A equals to this big. So basically this move and this move, and we get this A1 divided by 1.303 equals to this, and then equals to this, the throat, for the throat area. Okay, I think that's all from me. Thank you very much for watching. If I made a lot of mistakes, I'm very sorry for my sorry for my mistakes. Thank you very much for watching. Wassalamualaikum warahmatullahi wabarakatuh.